So, thank you. My name is Jae KIM, and today I'm going to talk about categorical syllogisms and also delve deeper into the relationship between different categorical propositions by using the square of opposition. So today I'm going to talk about logic, which is the study of such propositions, and we're going to go into a specific type of argument, which are categorical syllogisms. So let's first start with the basics. I hope that a lot of you have at least seen this line of reasoning once or twice, right? All men are mortal. Socrates is a man, thus Socrates is mortal. This argument is most time accredited to Aristotle, who was the student of Plato, who was in turn a follower of Socrates. And he is one of the earliest pioneers of abstract logic, right? Abstracting the form of valid argumentation to study what forms of argument are actually correct and which are false. And going back to propositions, so as I said before, logic is the study of propositions. But what are propositions? All propositions are statements with a truth value, simply put. And classically, we only have two truth values. So all propositions are either true or false. So for example, the first proposition, all men are mortal, I would assume that it's a true proposition. And the second proposition, Napoleon was not French. That would be an example of a false proposition. Okay. So we have many different types of propositions. And today we're going to focus mainly on categorical propositions, but just so that we can compare, I'm also going to briefly introduce conditional propositions. So categorical propositions are propositions that state the relationship between different classes. So for example, when we say that all snakes are reptiles, snakes can be seen as a class of different animals, right, that slither on the ground to lay eggs. And reptiles are also another class of different organisms that share a set of common traits. And the second example, some ignorance is blissful. We can see that to be a statement about the relationship between ignorant things or situations where you're ignorant and things that make you happy or things that make you blissful. So another type of proposition are conditional propositions. And conditional propositions are propositions that talk about the implication relationship between two propositions. So for example, if I say that if it rains tomorrow, I'll go on a picnic, we can see this to be actually two different propositions that are linked together, right? The proposition that it will rain tomorrow. If this proposition is true, then the latter one, I will go on a picnic, will also be true. And the same goes for the second example. If you are ignorant, then you will be blissful. So easily put, conditional propositions are basically if-then statements. Okay. Now let's go into the different types of categorical propositions. So all categorical propositions are either universal or particular. So universal propositions, they talk about all members of a given class. So for example, when we say that all snakes are reptiles or all bears do not lay eggs, we're actually talking about all members of a given class, not just some of them. And opposing to that, we have particular propositions which only talk about some members of a given class. And here we're being charitable with the definition of the word some, right? We mean at least one, if not all. So the proposition, some Koreans are Asians, that will be an example of a true proposition because, well, as we all know, all Koreans are Asians. It's required for you to be Asian if you want to be Korean. But by some, we mean at least one, maybe all. So thus, this proposition becomes true. Okay. Categorical propositions can be categorized into another two varieties, right? We have affirmative propositions, which talk about positive relationships between the given classes. So when we say that all snakes are reptiles, we are affirming a certain type of relationship. But there are also negative categorical propositions, and these are the propositions that talk about a negative relation between the given classes. So when we say that some Asians are not Koreans, that would be an example of a negative proposition. Okay. So now that we've seen the different types of categories that categorical propositions fall into, we can count that there are a total of 4 different combinations. Right? So the first 2 are the universal affirmative and the universal negative. So universal affirmative propositions take on the form of all S is P. So for example, all snakes are reptiles would be an example of a universal affirmative. And the universal negatives take on the form of all S is not P. So all cats are not dogs is a universal negative. We also have the particular affirmative and particular negative. So the particular affirmative would take on the form some S is P. For example, some students enjoy math. And the particular negative takes on the form of some S is not P. So for example, some actors are not talented. So we can organize these 4 different types of categorical propositions into a square, which we call the square of opposition. So the universals go on top while the particulars go on the bottom, affirmatives to the left, and negatives to the right. So the universal affirmative will be on the top left, the universal negative on the top right, and so on. We can actually abbreviate, or I'm going to abbreviate the different categorical propositions using the following rules. So using the Latin words for affirmative and negation, affirmo and nego, we're going to take the vowels from each of these words. So from now on, the universal affirmative will be A, the particular affirmative will be I, the universal negative will be N, and the particular negative will be O. The square can be visualized like so. Now that we have explored the different sort of categorical relationships, we can now go on to talk about the relations between these different relationships, which we can organize more clearly using the square. But to sum up, we have a total of 4 different types of categorical propositions, right? A, I, E, and O. So the first type of relation we'll have between categorical propositions are contraries. So contrary propositions cannot both be true, but can both be false. So A and E are contraries, right? If all S is P, we know that E, or all S is not P, must be false. And if E is true, A is false. But it can also be the case that both are not true, right? If some S is P while some S is not P, A and E are both false. And that brings us to subcontraries. Subcontraries are basically the opposite of contraries. So they can both be true, but cannot both be false. And I and O are subcontraries. Sorry, this is a typo. I and O are subcontraries. So we know that at least one of these 2 particular propositions must be true at all times, right? It's impossible for both of them to be false, but it's possible for both of them to be true. Next, we have contradictories. So contradictories are a tighter relationship between contrary. Right? Contradictories can be seen as a sort of relationship that fixes the truth value of one proposition given the truth value of another. So A and O, E and I, both are pairwise contradictories. Right? So if A is true, it must be the case that O is false. There is no other possibility. The same goes for I and E. If E is true, I must be false, and vice versa. Okay. So there's another type of relationship which we will call subalternation. So we call the universals superalterns and the particulars subalterns. Right? So if A is true, then I must be true as well. We will call that relationship subalternation. And the same goes for E and O. If E is true, O must be true. It's obviously the case that if all S is P, then the statement some S is P must be true as well. And using contraposition, we know that if the subaltern is false, then the superaltern is false, right? So summing things up, we're left with this square of opposition with all these different relationships between the categorical propositions. We can actually do a geometric analysis of these different categorical propositions to gain a different way of looking at these relations. So let's go on and do that. As I said before, categorical propositions are propositions that deal with classes, and we can visualize classes as circles. And there are a total of 5 different spatial relations circles can have with each other, right? They cannot overlap as they do in figure 1. One circle might be wholly included in another, as in figure 2, or the opposite situation might be happening as in figure 4. Or we can have something like figure 3, something that looks like a Venn diagram, where they do overlap a bit, but there are parts that do not overlap. And as you can see in figure 5, the 2 circles might completely overlap, or we can say that they are identical. Now we can repurpose or take another look at the 4 categorical propositions using this geometric lens. So for example, all S is P. This statement can be referring to either figure 2 or figure 5, right? We just need the whole of S to be included in the whole of P. Thus, we are left with these 2 possibilities. And for I, some S is P, we are talking about situations where at least some part of S is included in P. So that can be either figure 2, 3, 4, or 5. Right? In the case of E, we're saying that all S is not P, can only be referring to one of these 5 figures, which is figure 1, where they do not overlap at all. In the case of O, some S is not P, we're talking about situations where at least some part of S is not included in P. So it can either be referring to figures 1, 3, or 4. So using this, we can actually create another square of opposition by relabeling the vertices. So A is 2 or 5, I is 1, E is 2, 3, 4, or 5, and O is 1, 3, or 4. And this actually helps explain the different relationships as well. Right? When we look at the contrary relation between A and E, we see that they are mutually exclusive. Right? They do not overlap at all. However, they do not exhaust all 5 possibilities. Right? Figures 3 and 4 are not included in A and E. Thus, we know that while it's possible for both of them to be false, it's impossible for both of them to be true. And the opposite occurs with the subcontraries. Put together, the particulars I and O exhaust all 5 figures. We have 1, 2, 3, 4, and 5 wholly included. So we know that at least one of the 2 must be true at all times. However, we also see that they share some figures, 3 and 4, namely 3 and 4. So thus we know that the subcontraries can both be true, while both cannot be false at the same time. Subalternation also becomes self-explanatory because the cases that the superalterns are referring to are included in the cases the subalterns are referring to. 2 and 5 are included in the I case, and figure 1 is included in the O case. And the contradictories also, we can also shed some light on the contradictory relationships, because taken together, the pairwise contradictories wholly exhaust the 5 figures. So for example, with E and I put together, we have figures 1, 2, 3, 4, and 5. However, they are mutually exclusive, so we know that if one of them is true, the other must be false, and vice versa. Now, going back to the earlier line of reasoning that we looked at, all men are mortal, Socrates is a man, Socrates is mortal. We now know that these 3 statements are not just any kind of statement, but they are all categorical propositions. And I like to say that logic is the study of deductive relations between propositions. So in this case, assuming the truth of the top two propositions, which are called premises, we can deduce the necessary truth of the final proposition, which is the conclusion. Now, we call these sorts of arguments categorical syllogisms. Categorical syllogisms are a set of three categorical propositions, two of them premises from which we can deduce one conclusion. Another example can be seen in the following. All vegetables are good for you. All cucumbers are vegetables. Thus, all cucumbers are good for you. This is an example of a categorical syllogism. Now, all syllogisms share common traits. They share structural characteristics. And they typically all contain three terms. So in the following example, we see a number of recurring terms. There are a total of three that are shared throughout the three propositions: vegetables, cucumbers, and things that are good for you. And we can actually name all of these terms. Looking at the conclusion, we call the predicate of the conclusion, things that are good for you, the major term, which I'll now call P. And we call the subject of the conclusion, which in this case are cucumbers, the minor term, which I'll call S. And the term that appears in the premises but not in the conclusion is called the middle term. So in this case, vegetables would be the middle term, which I'll now call M. So using this, we can actually abstract the structure of syllogisms. But before that, we have a total of three propositions in syllogisms as well as three terms. And we call the premise that contains P the major premise, and the premise that contains S the minor premise. So the order of the premises do not actually matter logically, but traditionally, we put the major premise in front of the minor premise. So abstracting the structure of syllogistics, we'd actually count the number of distinct structures syllogisms can have. So we know that the first proposition will always contain the major term, which is P, and the second proposition will always contain the minor term, S. And we know the structure of the conclusion, S and P. So the only way we can actually reorganize the syllogistic is by reorganizing the order or patterns of middle terms. So they can go in a diagonal line, be aligned to the right, be aligned to the left, or going diagonal the other way. So we can see that there are a total of 4 distinct syllogistic figures. So we have the first, second, third, and fourth figure. We also have something called syllogistic moods. So each of the premises, the major, minor, and the conclusion proposition will have one of 4 categorical relations, right? When we say that all M is P, for example, the categorical relation A will be existent in that premise. So the syllogistic mood can be seen as a triplet of 3 letters. For example, AAA would be a syllogistic mood, or EIO would also be another syllogistic mood. And since there are a total of 4 distinct possibilities for each proposition and 3 propositions in a syllogism, there are 4 to the third, or 64 possible moods each figure can take on. And since there are 4 total figures, we know that there are a total of 192 possible syllogisms. But what about valid syllogisms, right? When we're talking about logic, we really want to know what forms of arguments are true or valid. So which of the 192 are valid? Well, for example, AAA-1 and EAE-1 are examples of valid syllogisms, right? So today we're mostly going to talk about the first figure, but in contexts where the syllogistic figure is not obvious, we actually denote the figure number using this notation, -1 or -2, -3, -4. And medieval scholars have actually come up with mnemonics so that they can memorize which syllogistic moods or syllogisms are true. So AAA-1 would correspond to Barbara, and EAE-1 would correspond to Solaren. Now, if you remember the square of opposition that we've just gone over earlier, you might remember that we talked about subalternation. So subalternation is the relationship between the universal and the particular. So A and E are both universal statements. And we know that if A is true, I is true. And if E is true, O is true. So from Barbara and Solaren, we can actually deduce two new valid syllogisms, Barbarie and Solaront. However, these two are often not included in the list of valid syllogisms because their conclusions are not as strong as they can be, right? We can say that all S is P instead of some S is P, right? So the I conclusion in Barbarie and the O conclusion in Solaront are considered too weak, thus less sweeping or redundant. So let's construct a example syllogism using the mnemonic Solaren. So Solaren or EAE is a first figure syllogism. So we know that the middle terms will be arranged in this order. And the mood in this case is EAE. So the categorical relations would come in this order, EAE. So we just need to substitute terms for actual terms. So let's say that good cars are the middle term for our syllogism, and cheap things are the term or the major term. So you can say that MEP stands for all good cars are not cheap. And if Ferraris are our minor term, that SAM would be all Ferraris are good cars. And from these two premises, we can conclude that all Ferraris are not cheap, or SEP. Pretty straightforward, right? We can actually show the validity or invalidity of certain syllogisms using a Venn diagram. So I said that categorical propositions were propositions that dealt with classes. And we saw that during our geometric analysis, the classes can be easily visualized using circles. So when we're doing a Venn diagram analysis of syllogisms which contain three terms or classes, we would need a Venn diagram with three circles, right? There's always going to be a minor term, a middle term, and a major term. So you can label the circles any way you want. But in the case of Solaren, we need to look at the premises first. So when we look at the premises, we always start with a universal premise. But in the case of Solaren, E and A are both universal relations, so we can start with either one. So starting with MEP, this states that all M is not P. Thus, we know that the area where M and P overlap, we know that this area does not exist. There is no such M that is also part of P at the same time. So we can just shade this in. And next we can go on to the second premise, SAM, or all S is M. So we know that all members of S must also be members of M, or all S is wholly included in M. So we can basically shade out all the area of S that is not included in M likewise. Right. Now the only thing we have left to do is examine the final proposition, SCP, or all S is not P. So we have seen that after we shaded it out, we can clearly see that all of S, this red shaded area, is not included in P at all. So we can conclude the validity of the syllogism Solaren using this sort of method of analysis. Okay. Now let's try doing this Venn diagram analysis on a wholly new syllogism. So since we're going to restrict ourselves to the first figure syllogisms, let's look at IEO. So at the current moment in time, we don't know if IEO is a valid syllogism or not. but we can find that out using this analysis. So the M middle terms will be arranged in this fashion, and the IEO relations will come in this order. And we basically do the same thing. But in this case, we know that I is a particular relation while E is a universal one. And as I said before, we always start with the universal relations. So we start with the second premise, SEM. All S is not M. So we know that S and M do not overlap, or they should not overlap. So we can just shade in this area where S and M overlap because we know that this space does not exist. And going back to the first premise, MIP, this states that some M is P. I'm sorry. This is actually a typo. It's not IEO, it's actually supposed to be OEO. I'm very sorry. But as you can see in the Venn diagram, we can say that some M is not P. If we fix the I to be O, then we don't know if it is the case that the overlapping region is void, right? So it might still be the case that some M is P, but we know that there is at least one object that is a member of P that is not in P. I mean, there's at least one object that is a member of M, but not a member of P. So we can refer to the existence of that object using this red cross right here. Now that we have done all the markings, we can go on to examine the conclusion of the syllogism, SOP, or some S is not P. Now we can clearly see that no distinct or particularly useful relation has been established for S and P, right? They're basically the same, they're in the same state they have been from the beginning, right? They might overlap, they might not. These white areas are totally indeterminate. We don't know if they have members or not. Thus, we can conclude that this syllogism is not valid, right? It does not tell us anything about S and P. Now, okay. Are there any questions so far? No questions? Okay, so actually compounded a list of related topics to the square of opposition and categorical propositions for those of you who might want to look further into this. All right, you can search one of these terms up on Google if you want to learn more. But before going on to that, let's go on to some comprehension level problems. Oh. So any one of you can answer by unmuting your mic. How many distinct types of logical relations exist between categorical propositions?
Was this 192?
Excuse me? Oh, we have stated that there were 192 possible syllogisms, but how many distinct types of relations exist between propositions? If you recall back to the square of opposition, we talked about different relations like contraries, contradictories, etc.
I think
I'm sorry, your sound is too low.
I think it's 3.
3?
There were 4.
Yeah, 4, right.
Four.
Yeah, there are 4. There are contraries, subcontraries, contradictories, and we also talked about subalternation. So there are a total of 4 relations. Okay. So next question. Which categorical relations are symmetrical? And by symmetrical, I mean something they can see in the equal sign. If we say that A equals B, then we also know that B equals A. So
3.
3. Any more guesses?
I think it's 2.
2. Which ones? Which ones are symmetrical from A, I, E, O? So let's look at this from the geometric perspective again. So because it's actually easier to look at symmetry when we're looking at shapes. So going back to the 5 figures, we said that A, all S is P, might be referring to either one of these 2 figures, right? So we see that S and P are in a symmetrical relation in figure 5, but they're not symmetrical in figure 2, right? So since A is either 2 or 5, we can safely say that A is not symmetrical, right? Even if all S is P, it might not be the case that all P is S, so A is not symmetrical. In the case of I, we're saying that some S is P. So we're talking about one of these 4. And while figures 3 and 5 are symmetrical for S and P, figures 2 and 4 are not. But actually, put together, when we put together figure 2, 3, 4, and 5 as a whole, we actually do have a symmetrical relation. As you can recall, I actually talks about the overlapping region. Actually talks about there being at least some overlapping region between S and P. So as long as that region exists, I is true. And since that region is part of both S and P, regardless of which one is bigger or if they're identical, I is also a symmetrical relation. Now, E, it's very easy to see that E is a symmetrical relation because S and P are in a likewise state. Now, O, some S is not P. So it's very easy to see that O is not a symmetrical relation because we have figure 4 where the whole of P is included in S. These 2 are not in symmetrical relation. Thus, O as a whole is not symmetrical. So yes, the correct answer is 2. We have E and I, a total of 2 symmetrical relations. Okay, the next question. True or false? The proposition some S is P implies that some S is not P.
It's true.
True?
Yeah.
Any other guesses?
No,
No. Why is it false?
because all S can be P.
Yes, that's exactly the case, right? We said that we were being charitable with the definition of some. It's at least one, if not all. So some S is P might be referring to a situation where all S is P, in which case some S is not P is not true at all. Thus, this causal or conditional relation between the 2 propositions do not hold. Okay. So which of the 4 figures does the following syllogism belong to? All math problems are not easy. All physics problems are easy. All physics problems are not math problems.
E.
Yes, that's the correct mood, but which figure does the syllogism belong to? We talked about 1. Any other guesses?
All math problems are not easy is E. All physical problems are easy is A. And all physical problems are not math problems is O.
Okay, so I think a lot of you are confusing between figures and moods. So figures were the arrangement of the middle term, right? So in this case, the middle term are easy things. Easy things are the middle term. They appear in the premises, but not the conclusion. And we can see that the middle term is aligned to the right, right? So middle terms that are aligned to the right are figure 3, if you guys can recall. Figure 1 was when the middle terms were aligned in a diagonal from the top left corner to the bottom right. And figure 2 was when the middle terms were aligned to the right. Oh, I'm sorry. This is actually figure 2. And figure 3 was when middle terms were aligned to the left, etc. Okay. So yeah, the mood is, of course, EAE, but the syllogism figure number is 2. So follow-up question, is the following syllogism valid? Is it true? Any guesses? Is it valid or invalid?
It is valid.
Yes, it is actually valid. I was actually trying to make you prove it, but I think there is no easy way. Can you try to explain it? Why is it valid?
Because since all math problems are easy and all physics problems are not, they're part of different, like they're already mutually exclusive. So since their supersets are mutually exclusive, since they're the subsets of those, they're, yeah, that's why.
Yeah. That's basically it. But a very simple way of explaining it, if you know all the valid syllogisms, would basically say that EAE-2 is an example of a valid syllogism, thus the following syllogism is true. Right? That's the power of abstracting forms of argument. Right? Once you know all the valid forms of argument, you can actually deduce conclusions about the validity of specific arguments like this one. So question 5 was supposed to be an exercise where you use a Venn diagram analysis method to prove the validity of different syllogisms, but in this medium, this is actually impossible. So I'll go on to question 7. So which categorical relations are distributive and for which term? Though this can actually be pretty hard for those of you who do not know what a distribution of terms are, but distribution is basically when a categorical relation talks about all members of a given term. So for example, when I said that all Koreans were Asians, the categorical relation we have in that proposition is A, right? The universal affirmative. And in that proposition, we're talking about all Koreans, right? Each and every one. So in that proposition, the term Koreans is distributed. And when we say that all bears are not reptiles, the term reptiles is being distributed because we're saying that bears are not snakes, bears are not lizards, bears are not dinosaurs, etc., etc. So, yeah. Which of the 4 types of categorical relationships distribute at least one term? Any guesses?
I think E.
Okay. Yes, E is a distributive relation. Is there another one? There are 2 more. So an easy one is A, right? The universal affirmative, because it's obviously distributing the subject of that proposition. When we say that all snakes are reptiles, we're talking about all snakes. So snakes will be distributed. So far, A and E are distributive relations. Is there another one? I mean, there is another one, but which one is it?
It's O.
Yes. Why is it O?
Because like the if they say like some wait I don't, because of like it, the rule applies to every member of the group, like everything in the group.
Yes, that's true. So whenever we have a negative relationship, the thing that we are negating, we're excluding all of it, right? When we say that all S is not P or some S is not P, we're actually referring to all members of P because we're excluding all of them. So E and O, the negative propositions, are both distributive, and A is also distributive. Okay. So this is another sort of further development question. What do you think of this? If the proposition all unicorns have horns is true, then is the proposition some unicorns have horns also true?
Yes.
Can you
Yes,
explain
because
your, yeah.
because some unicorns can be all.
Mm-hmm.
That's why that statement is true.
Okay, so yes, we can refer back to the self-alternation relation between A and O. But like intuitively, do you think that propositions about non-existent things like unicorns can ever be true?
Based on what we know about them, yes.
Can you like explain your reasoning?
Like, let's say that we're looking at a myth or something. We basically created it. So like, if we look at the information that we made for ourselves and it's true, then I guess it can be true.
Okay, but in that case, we're actually, in the case of stories or made up things, we're actually talking about existence or existence within the scope of that made up narrative. But in this case, we're talking about unicorns having horns, right? We all know that unicorns do not exist. At least I think they don't exist. But we do know that horns as a class of object do exist. So how can an imaginary creature like unicorns actually possess an existent object like a horn?
Logic doesn't apply the same way to non-existent entities like that as to real objects like that. Maybe it's like that.
Okay, so wait, I'm sorry. Your sound quality was not good, but what's your answer to this validity question?
I think it's false because for non-existent entities, maybe logic doesn't apply in the same rules and format as it does to real entities like other animals like horses, humans, and stuff like that.
Yeah.
Just my opinion.
Yeah. So actually, there are many different ways to approach this question, right? There is no set answer, and we often call this problem the problem of existential import, right? So what happens when we have terms that do not have, oh, we call this the extension of a term, but what happens when we have classes that do not have actual members, right? Like unicorns or chimeras, non-existent things. And in a system of logic called Boolean logic, we say that only the particular statements have existential import, meaning that statements I and O, some S is P and some S is not P, those two propositions require the terms to have extensions, or S must have members for I and O to be true. So in the case of Boolean logic, all unicorns have horns would be a true statement, while some unicorns have horns would be a false statement. So through the lens of Boolean logic, subalternations as a relationship between categorical propositions actually disappears. The square becomes dismantled. And when you go further into the modernization of the square proposition, which is a creation of classical logic, when we reformulate the categorical propositions as through modern formal logic, all of the relationships that we've just talked about, or most of them, actually disappear. The only relationship left are the contradictories. So contraries, subcontraries, and subalternation stops to function as they should. Right? There are cases where both A and E are true, and there are cases where both I and O are false. And as we've just talked about, there are cases where the superalterns are true, but the subalterns are false. So that's actually it for today's lecture. But do you have any further questions about the topic? No questions?
Yes. Okay. Thank you, Minjae. That was a great lecture.